Like I said a second ago, we're going to dive into Chapter 4 now, which has to do with diodes. Really the same component as a PN junction, but now we're going to be looking at it from a larger, more circuit-based, big picture view. So in this chapter, we're going to learn about the characteristics of an ideal diode and how to analyze, as well as design circuits that contain one or more diodes together with resistors and DC sources, and we're going to use those to solve problems. We're going to talk about the details of the VI characteristic of the junction diode, which we derived in Chapter 3. We're going to talk about how to use it to analyze larger circuits based on the bias regions forward, reversed, and breakdown. We're going to talk about a simple but effective model of the diode. So there's essentially this chapter follows a similar structure. 4, 5, and 6 are all the same. Where what we do is we introduce a device, whether it's a diode or a different type of transistor, and then we talk about how there's different models that can be used to represent it, and those models have pros and cons. Okay? Some are simpler and are easier to apply, meaning that it'll reduce the computational complexity, but they're less accurate, so the answer you get will not be as good. Then you have more complicated versions of the model, which give you a more accurate answer, but we can't solve them using our, circuit analysis methods that we present in ELC251-10. So one of those models is the constant voltage drop model for the diode, which that doesn't mean anything right now, but it will. We'll talk about something called the small signal model. So the small signal model is obviously another type of model that is applied to, it's almost like a linearization, where we're looking at how the effect of small changes in the input how it affects the output. Small signals. We're going to talk about the use of forward bias diodes, and then reverse bias and breakdown region. We're going to talk about the application of the diode in the design of rectifier circuits to convert AC voltages to DC as needed for powering electronic equipment. And then we're going to talk about a whole bunch of different applications. So to make a long story short, we're going to talk about, we'll sort of reintroduce the diode. We're going to talk about several different models that we can use to analyze the diode. Ideal model, constant voltage drop, small signal, exponential. Then we're going to talk about a whole bunch of different applications. There's Boolean gates that we can create using the diode, the rectifier, voltage regulator, all kinds of different stuff. So very practical chapter. So let's start from the beginning, which is the ideal diode model. So this is the one that really you're going to be using a large percentage of the time. In the ideal diode model, we consider that there's really just two modes of operation, on and off. Okay? And what that means is that if the voltage across the diode is reversed, then there's no current flowing through it. If the current flowing through the diode is forward, then there's no voltage across it. It just goes from short circuit, open circuit, short circuit, open circuit, like a switch. Now, as we know, that's not a completely accurate description of how the diode works because the actual model looks more like that, but you can see how this approximation it's a rough approximation, right? So we have two modes of operation. We have a device symbol, which many of you have already seen before, this triangle with a line, and it has a cathode and an anode. We assume that the current is flowing as the triangle points, or as the arrow points. Okay, now when we're using the the ideal diode model, external values must be used to limit the current. So let's say this resistor weren't here, and I apply 10 volt across the diode. It's going to be forward biased, which means the amount of current flowing is essentially going to be infinite, at least according to the ideal diode model. Now, will the amount of current be infinite for a real diode? No, because there is some internal resistance. But if we're using the ideal diode model, it's the external values that will define the current flowing across that diode. So in this case, right here, if we're using the ideal diode model, we have 10 volts over 1 kilo ohm and no voltage drop across the diode. It's forward bias, so it becomes a short circuit, and so that's why we have 10 milliamps. 10 volts over 1,000 gives us 10 milliamps. Similar thing over here. Actually, well, this one is a blocking case, right? We have 10 volts. This reverse biases the diode, which means there'll be no current flowing, 0 milliamps. That means there's no voltage drop across this resistor, and the full 10 volts is applied across the diode. Okay, so before we get into all the different types of models and that type of stuff, let's start off taking our easiest model, our simplest model, which is the ideal, and let's apply it to a circuit that actually does something, okay, which is the rectifier. Have you all heard the name rectifier before? Right? Okay, good. So a rectifier, again, what it does is it takes an AC voltage and it converts it to a DC. And this is a half-wave rectifier. And what that means is it takes our AC waveform, and instead of flipping the bottom up, it only gives us half the wave. So it'll be signal, no signal, signal, no signal. A basic half-wave diode rectifier can be built just using a single diode as shown here. So this would be an AC source, this is your ideal diode, and this is your load. So how does this circuit operate? Whenever VI is greater than 0, the diode will conduct, and VI will be the same as VO. Whenever VI is less than 0, the diode will block, and VO will be equal to 0. All right. So now let's take a look at an example based off the half-wave diode rectifier, but with a little bit of a twist on it, which affects the way that we solve. So now we have a Thevenin source, so it's a voltage with a series resistor. We still have this diode, and now you can imagine this like a circuit that we use to charge a battery, okay? So this is a DC voltage here that we have. Now, if we were using this to charge a battery, it would make sense, right? What we do is we set the diode pointing to the right. That way, we can only have current flowing into the battery, right? It doesn't allow us to accidentally discharge the battery during the negative cycles of the AC wave. So part A asks us to find the fraction of each cycle during which the diode conducts. So let's take a look at this picture right here. First thing we start off with is the input wave itself. It has an amplitude of 24 volts. Now, let's try to figure out where the cutoff is for the diode, okay, when it's going to switch on and off. We know that the changeover from the forward bias to the reverse bias is going to happen when the current through the diode is 0, when it first reaches 0. Okay? So when is that point going to be? When is the current here going to be equal to 0? So if we have Vs minus 12 over 100, and there's no internal resistance here. So Vs minus 12 over 100, when is that going to be equal to 0? It's going to be equal to 0 when the value of Vs is 12. So you can see here, that's the reason why we're drawing these intersections. When the input, Vs, reaches 12, that's going to be the changeover from open, close, open, closed. All right? Now, we know that when Vs is greater than 12, the voltage here will be, or the current will be in the forward direction, which means this will be short-circuited. And so the current, some current will flow. We haven't calculated what that value is. When Vs is less than 12, the current will be reversed, meaning, or the current will be pulling in the reverse direction, which means this will block, and essentially no current will flow. So what we have determined so far is that we have a small window whenever Vs is greater than 12, within that window, that's when current will flow. The other part of the cycle, we don't have any current flowing. So all the way from 12 going down to negative 24 till it gets back to 12. Now, so now we need to solve for the actual numerical answers. Okay. And here you can see some of the math, right? I said ID is equal to Vs minus 12 over 100. That's just taken directly from the circuit. And so this is what is going to define this curve right here. So this curve is equal to Vs minus 12 over 100. And the shape, it mimics the cap of the Vs. ID is equal to 0 whenever Vs is less than 12. Remember here, at this intersection, the current is equal to 0. That's how we know it's the changeover point. Okay, so how do we figure out what those intersections are? They ask us for the percentage, the fraction of each cycle during which it conducts. So we want to know how much is this divided by that. What percentage is it? So in order to do that, what we want to do is we want to figure out when 24 cosine theta equals 12. Right? This is our input. We could use sine or cosine, it doesn't matter. Okay? So amplitude 24 cosine theta equals 12. What's theta? Essentially, there's two values of theta that apply because, right, there's 2 points at which 24 cosine theta will be equal to 12. The difference between those points is going to be the conduction interval. So when we come up with those angles, what we see, it's inverse cosine of 1/2, and the answer is plus or minus 60 degrees. So therefore, when we solve for the length of the conductance interval, it'll be 60 minus a negative 60, which is 120 degrees. And when we find the fraction, it'll be 120 degrees over the total, which is 360 degrees. And so 1/3 of the period. Okay? Or if you want it in terms of time conducting, it would be 1/3 times the period. Yes?
What do you mean by conductance interval?
So the conductance interval is the interval when the diode is conducting. So we'll call, yeah. Well, it's that little, yeah, it's this part of the x-axis. This is the conduction interval. This would be the blocking interval. Okay, so the next part, so we answered the first part of the problem. The next part of the problem asks us to find the peak value of the diode current and the maximum reverse bias voltage. So let's put off the second one for a second, and let's talk about what's the peak current going to be. So we know where that's going to occur. It's going to occur when Vs is at its peak. And so we can just go ahead and use the expression we already developed right here, plug in a value of 24, and that will give us 120 milliamps. So 24 minus 12 divided by 100 gives us 120 milliamps. Again, right, it's minus 0 volt drop across the diode because we're still using the ideal diode model. Now, what's this one asking? The second part of the problem, it says, what is the maximum reverse bias voltage that appears across the diode? So what does that term mean? It asks us about the maximum amount of voltage that the diode is asked to block. So obviously it's not blocking at all during the conduction interval, so we're just looking at the blocking interval. So let's start right here. What is the reverse bias voltage across the diode right here? It's 0, right? Because we have 12 and 12. So that'll be 12, 12, 0. As Vs becomes more negative, there will be a reverse bias voltage that appears across the diode, and that'll get bigger and bigger and bigger until it reaches its peak. So the magnitude of the reverse bias voltage is the difference between the black and the blue. And you can see that the maximum will be down here when the Vs peaks as a negative. So it'll be 24 minus 12. Or actually, I should say 24 minus a negative 12 for a magnitude of 36 volts, right? Because it has to block both, right? The 12 plus the 24. And we're saying negative 36. You could also say the magnitude of it is positive 36 volts. Essentially, when you say reverse bias voltage, you're implying that that is a negative, it's a negative voltage applied across the diode. So even if you said positive 36, honestly, I would consider that a correct answer because the term itself implies that it has to be a negative value. Okay, so now continuing with this theme of talking about applications. We talked about the half-wave diode rectifier. Let's talk about some other useful application, which is a logic gate. So, right, we can build an OR gate and we can build an AND gate using diodes. So let's take a look at how this might work. So for the OR gate, what you have, voltage is applied right here. We're going to assume it's 0 or 5. 5 being a logic yes, high. 0 being a logic no or low. And so let's see what happens. First things first, what happens when you don't apply any voltage here? If you don't apply any voltage, what that means is that we'll have, the circuit will be dead, essentially, and therefore the diodes will block. And what you'll end up with is 0 volts at the output. There'll be no current flowing through here. That means R times I will be 0, and so your output will be 0. Right? The current flowing right here is the sum of these three currents together. Okay. Now, what happens if we turn on any of the three? So let's say we make this 5 volts. 5 referred to ground is positive, so this will start to conduct. We're using the ideal diode model, which means that when it's conducting, it's a short. So the voltage here will be the same as the voltage right here, which will give us a 5-volt output. What's going to happen to VC and VA? Right, this will be 5, this will be 0, 5, 0, so both of these diodes will block. So you see that this functions like an OR gate, right? Any of the three, if we turn them on, it will raise the output voltage to 5 volts, or it could be 3 volts actually, whatever you use. 1 out of 3 does the same thing as 2 out of 3 as 3 out of 3. Doesn't matter. And that's, again, that agrees with how we expect an OR gate to work. If any diode conducts, then Vy equals 5. Now let's take a look at an AND gate. AND gate's a little bit different. So now let's look at the case where, again, all three are 0. So if this is 0, 0, 0, okay, then we know that these diodes will all conduct, right? We have 5 volts minus 0 volts. This will be forward biased. This will conduct. And what that'll do is that will set this value, this voltage here, short it to ground. And so you won't get anything out. Okay, now let's look at the case where only one of the 3 diodes is shorted to ground. Okay? So let's say, and we'll look at these individually. So let's say that this was 5, 5, and 0. Okay. This 5-volt potential here will cause this diode to block, right? It'll be a 0-volt differential across the diode. It'll block. This will also block. So you can almost imagine it not being part of the circuit at all. And then VC, with a value of 0, that will do the same thing as our first case. It'll short it to ground. And so we'll have a ground here at 0 volts. So what you see is that, again, agreeing with how we expect an AND gate to work, if any of these 3 values is 0, the output is going to be 0. The only case where we get a 5-volt output down here is when all 3 of the diodes block. So if it's 5, 5, and 5, right, or some value greater than 5, block, 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 which means no current flowing along this path, which means that the 5-volt will be applied down here, and it'll give us 5 volts. So doing these diode problems, especially when we're employing the ideal diode model, it's again goes back to just regular old circuit analysis. Because the ideal diode, it just is represented as short circuit, open circuit, short circuit, open circuit. And when you're doing this type of analysis as part of your homework on your own, it may make sense to redraw this circuit for the different cases, putting in short circuits and open circuits. I think that helps. So that's the basics. Another example application, which is using the diodes to create these logic gates. Okay. So in the beginning of the chapter, we do jump around a little bit, but we'll start to get into more of the in-depth modeling issues in a second. But right now, we're still talking about the ideal model. And so let's talk about one difficulty that we're going to see, which is essentially circuits that have lots of diodes. Even for the logic gates, it was a little bit difficult to analyze what was going on because there was more than one diode. The halfway rectifier was easy. When you only have one diode in a circuit, you can solve for the rest of the circuit, and it will tell you exactly whether that diode is blocking or conducting. You should know. Okay? When you have more than one diode, what happens is one affects the other, and the other affects the first one. So if you take a look at this circuit right here, you don't know right off the bat. There's no way to know right off the bat whether diode 1 or diode 2 is conducting or blocking. And so that's the problem. When we say what's the difficulty associated with multi-diode circuits, it's the fact that the circuit cannot be solved without knowledge of the diode's status or mode of operation. However, we don't know the mode of operation because it's dependent on the solution. We don't know the solution without the mode. We don't know the mode without the solution, vice versa. Okay? So that obviously is a problem. So how do we solve something like this? Essentially, we're going to assume the status of the diodes. Open, closed, forward bias, reverse bias. Then we're going to solve, and that could involve mesh or nodal analysis. It could just be some simple KVL, KCL based solution. Then what we're going to do is we're going to check for coherence. And what that means is, in the beginning, whatever diode that we assumed was conducting had better have a forward current flowing through it, not reversed. And any diode that we assumed was blocking better have a reverse voltage, a negative voltage applied across it, not a positive one. If either one of those criteria for coherence is broken or not satisfied, then what that means is we have to start all over and change our assumptions. Okay, so how do we begin? We'll start with a plausible assumption, and then we'll, like I said, we'll check it to see if it works. So let's solve part A first. We have 10 volts, 10 kiloohms, 2 diodes, a ground, 5 kiloohms, and negative 10 volts. And we're going to start off by assuming that D1 and D2 both conduct. So what that means is this is a short, this is a short. Point B is connected to ground, and this, right, we have this current flowing here. Now, once we make the assumptions, hopefully, right, the math should be very easy, especially this is not a very complex circuit. So we can go ahead and solve. We know that VB is equal to ground. We know that ID2, which is this current here, will be equal to 10 minus 0 over 10,000. So that gives us 1 milliamp. Then we'll also know that this current right here, which I'm calling IR, will be equal to VB minus a negative 10 over 5K. So that's 0 minus a negative 10 over 5,000, and that gives us 2 milliamps. So if this is 1 milliamp and this is 2 milliamps, then we have a leftover of 1 milliamp flowing downward. And we can solve for that using KCL. Okay, so we solved. Is it coherent? We assumed that both of the diodes were forward biased and conducting. So now we have to check, are the currents through them flowing in the right direction? Is the current ID2 flowing in the right direction? The reference direction is down and the value is positive, which means yes, okay? The reference direction for this one is down and the value is also positive, so again, yes, so good. So that's coherent. So we're done. So that's the answer for part A. Now let's try part B. So we'll start off with the same assumption. Conducting, conducting. So we know again VB is equal to 0. This current here will be 10 minus 0 over 5,000, which is 2 milliamps. This down here is going to be 0 minus a negative 10 over 10 kiloohms, which gives us 1 milliamp. So we have 2 and we have 1, which means that the difference is negative 1 milliamps. Okay, so is it coherent? Which one is the problem? Exactly, right? The reason being that the reference direction is downward, the value is negative, so we are saying that this diode is conducting, but it has a reverse current, which is not right. This one's fine. So what can we do? I mean, it's not guaranteed that this will always work this way, but it makes most sense logically to flip the assumption that was the wrong one, right? So what we'll do is let's try it again, assuming that D1 is blocking. Okay, so now if D1 is blocking, this whole part of the circuit is gone, right? There's no longer a connection between this ground and B, and so therefore we can calculate the total current as 10 minus a negative 10 over 15 kiloohms, because this is a short. And so that will give us 1.33 milliamps flowing downward. And then VB is 1.33 milliamps times 10,000 minus 10, if we apply KVL right here. And so that gives us 3.3 volts. Yes?
With that assumption, are we assuming D1 is blocking or D2 blocking?
D1. Because D1 was the one that was problematic in the first pass-through of trying to solve it. So we flipped the assumption for that one. Again, there's no guarantee that that's going to work. You could have to flip both, but it's the most logical starting point. So now, is it coherent? It is, right? Because the current flowing with this reference direction downward, the value is positive. That satisfies the forward bias constraint. For this one, what we need for a reverse bias voltage to exist, which means that the voltage here has to be greater than the voltage here, and it is 3.3 minus 0. So that is an example of a multi-diode problem. As you could imagine, there's as many versions under the sun as you can think of, right? You switch around the resistors and everything, but the basic process remains the same. Define your assumptions, replace the diodes with open and short circuits, solve, check for coherence, and if you got to do it again, then you got to do it again. Okay, so this is a little bit more of a detailed look at how the diode works. We haven't discussed the breakdown region yet. We didn't discuss that at all in Chapter 3. For better or for worse, we didn't really go into the physics and the science behind the breakdown region. But a diode is not going to block forever. There's going to be a point where the magnitude of the electric field that you're applying overcomes the barrier against it and current begins to flow. So we really have 3 or 4 different regions that we have to look at when it comes to the diode. Obviously, we have the forward biased region. This can kind of be split up into the forward biased region and what we call, forward bias we also call the conducting region. So we have conducting and then what we call fully conducting, right? Because in this part, we're conducting, but you would not consider this to be a short circuit right here, right? This is not very much current flow. Over here, this is what we call the fully conducting region. Then obviously you have your blocking reverse bias, and then you have your breakdown reverse bias. And that's for when V is much, much less than 0. Normally we call this voltage here the Zener knee voltage, denoted by V sub Zk. One thing I will point out, the reason why there's a weird bump here is because they changed the scale going from the right-hand side to the left-hand side because they wanted to show there was some reverse current. But in reality, if these were on the same scale, it would just look like that. I feel like this is actually more confusing the way that they drew it than it would be otherwise. All right, so equation 4.1, restatement from what we've already seen from the end of Chapter 3, the exponential model for the diode's behavior. I equals Is e to the V over Vt minus 1. The thermal voltage is defined as Kt over Q, 25.8 millivolts at room temperature. Certain problems will also use 25.9 millivolts. And then here, 4.3 is a simplification of this expression up above. Again, we said that we'll use that when V is significantly larger than Vt, and we set that threshold at approximately 250 millivolts. Okay, the forward bias region, continuing on with that, if we assume that we don't have the minus 1, then this is an inverse expression for V and I. So you can calculate V from I. But again, this only works going down to where V approaches 250 millivolts. And so this relationship, what it shows us is that we have huge increases in current that are associated with very small changes in voltage. And that is reflected in the graph here as well, right? This is not an asymptote, okay? The voltage does not approach a value here, okay? It just keeps increasing at an ever more steep rate. So if you wanted to get to 0.8, to 1 volt, to 100 volts, you can eventually make it there, but the amount that your current will have to increase gets astronomical. All right, so there's one question that's asked in the book. It says, what's the relative effect of current flow on forward bias voltage? And so we did this example here. So if you take a look, I set up two versions of the exponential model. One is I1 with a voltage of V1. One is I2 with a voltage of V2. They're nondescript values. They're just generic. So let's say we divide one by the other. We can get rid of the IS's. We can combine the V's together. And then we can actually solve for V2 minus V1. We apply the natural log and do all the appropriate math. And what we see here, again, right, is that a 10 times change in current affects as little as a 60 millivolt change in voltage. So that could be going from 1 amp to 10 amps. Yeah?
Step 4, where you say invert this expression, how exactly is that?
Well, the steps are actually a little bit off because this is saying the result of what you just did. So you invert this expression to get this. And then you, from here to here, you convert log base 10 to, or natural log to log base 10. So it's a little bit weird. I probably should have put this step here and this step here. It's almost like one below where it should be. Because going from here to here, that's where you actually invert it. Going from E to the, and then converting that to natural log. Okay, so again, right, we have this fully conducting region, which is shown in green. I already talked about that. We also have a value we call the cut-in voltage, which sort of marks the beginning of the fully conducting region. It depends on the diode that you're using. We're going to say it's somewhere between 0.5, 0.6 volts. But really, if you want to effectively, reliably apply the ideal model, you want to have voltages that are going like 0, 5 volts, 0, 5 volts. Anytime you're really down in this range, using the ideal diode model, as we'll see, is not going to be your best option. For smaller voltages, you need to use the exponential model and actually capture what's going on right in here. For very large voltages, again, this is going to compress down and look like just a straight line. Example 4.3 is pretty similar to 4.2. I'll ask you to just take a look at that from the textbook. All right. So we have danced around the topic of the reverse bias region. We haven't really addressed it head on. As we know, the reverse bias region of operation is when the voltage across the diode is negative and it blocks. So we can use our same exponential equation, and when V becomes negative, what you'll see is this component here will get very small. Right? The larger V gets in magnitude, the smaller this gets, or actually closer to 1 that this gets, right? Because e to the 0 would be 1, so you have 1 over 1. So the closer to 1 this will get, and you'll be left with your I equals negative IS. So for very large reverse bias voltages, assuming we haven't entered breakdown, which is a separate thing altogether, we'll have I equals negative IS. Again, when V is very close to 0, we really need to include that minus 1, okay, in order to get a good picture of what's going on. And that applies on either side of the 0. The positive voltage needs to be greater than 250 millivolts. On the negative side, also needs to be a little bit bigger than VT. So a real diode exhibits a reverse bias current that's going to be bigger than what you would expect from IS. I said that in Chapter 3 as well. And this is attributed to leakage effects and imperfections in the way that the diode is manufactured. So if you were to characterize the forward bias current, you could essentially model it to the exponential structure, and you could extract what the IS value is for that diode, right? You take data points, you do a regression, you come back with a value of IS. And then you say, well, that should be the same value as the reverse current. Then you flip the voltage, and it's not. And the reason for that is these leakage effects and some imperfections in the diode. All right, so the breakdown region. The breakdown region is when the voltage, reverse voltage across the diode exceeds this Zener knee voltage, and it begins to conduct current in the reverse direction pretty quickly. Normally this is non-destructive, and what that means, does anybody know what non-destructive means?
Don't let the magic smoke out.
Yes, you're right, it does not pop. So now if you drive this current too high, then it'll heat up and then it'll pop, but you can go back and forth here without destroying the device. In fact, there are certain applications where that is part of the desired operation of the circuit. Okay, so let's take a look at this here. This like breaks down a whole bunch of different thresholds. So what we see is that the model I equals IS e to the V over VT minus 1 works all the way from here to here. It works for the forward, the reverse bias, and the region in the middle, okay? Which, excuse me, which contains both forward and reverse. Okay, it doesn't apply to the breakdown region. Our model doesn't take that into account. All right, now what this green is, the green is the area where you need the minus 1. Once you get to V is greater than 10 times VT over here, we can get rid of the minus 1. Once you get to V is less than negative VT, again, we can get rid of the minus 1. So over here, I equals IS e to the V over VT. Over here, I equals negative IS. And in the middle, you use that. Okay. So the previous slide defines, well, I wouldn't say it's a robust set of diode models, but it shows the different regions of operation for the exponential diode model. So far we've talked about two. We talked about the ideal diode model, which is open, closed, open, short, right? That's the ideal diode model. And then the exponential diode model, which is the one with the whole curve. So we've talked about this one. We've talked about this one. We have not talked about two others, which is constant voltage drop model and small signal or linearized model. And so that's what we're going to spend some time over, in the upcoming material talking about. I don't think I need to talk about this anymore. Exponential diode model, we know how it works, the pros and the cons. It's the most accurate out of the ones that we have looked at. It's also going to be difficult to employ in circuit analysis due to its nonlinear nature. So all of the mesh analysis, nodal analysis, all that type of stuff are all linear algebra. Right? Solving them is based on linear algebra. Linear algebra works for linear systems. This is nonlinear. You're not going to be able to define this as an impedance and fit it into a Y-bus matrix and all that type of stuff. So solving a circuit that has one or more diodes that need to be represented by this model is not going to be easy. So let's take a look at an example of that. So let's say that we want to solve this circuit shown to the right. VDD is 5 volts. This is 1 kilo ohm. And this diode right here, this is a way that they will often describe it in the book. Instead of giving you the IS value, what they do is they give you these rated values. They say at 0.7 volts, it throughputs 1 milliamp, and so you can use that to go back and get your IS value. Okay, so how do we calculate what is the current flowing through this flowing through this circuit? There's two different methods that we're going to look at. One is a graphical method. One is an iterative method. As you can imagine, the graphical method is a little bit rougher, but you can do it with some by hand. The iterative method is more mathematical. It's more practical for implementation in MATLAB or using some sort of a computer algorithm. So how would we solve this problem using the graphical method? So essentially, what we have to do is we have to plot the two constraints that dictate this circuit and the way that it works. So what are the two constraints? The two constraints are, first, ID has got to be equal to VDD minus VD over R, right? That's the first constraint. That is KVL, physics tells us that's got to work. The second constraint is that ID has got to be equal to IS e to the VD over VT minus 1, right? And so that is the difficulty of solving a circuit that has an exponential model. Inside of it is that we're trying to satisfy these two different constraints, not just solve one. Okay, so what we're going to do is we're going to graph both of these. And so this here is the load line. This is VDD. The second constraint is this, that ID must be equal to IS times e to the VD over VT minus 1, the exponential model. So this right here, this line represents the load, or the KVL, right? So VDD minus VD over R. This is the current associated with that. And then this here is the other constraint, which is ID equals IS times e to the VD over VT minus 1. Anyway, you get the point. Okay, so using the graphical method, what we do is graph both of them and simply just look for the point where they intersect. Okay, for this system, there should only be one intersection. And what this point tells us is that this is the only point where the physics satisfies both parts. And so that's the point. And then, you have to have some way of estimating where this is on the x and y axis. If you do it in MATLAB or using a graphing calculator, you could actually get the intersection. If you were doing it by hand, you would have to eyeball it. Anyway, so that's the graphical method. The pros, it's intuitive because of its visual nature. There's a lot of cons. Unless you're using a graphing calculator, it gives you relatively poor precision. It's not really practical for complex analyses because the more elements you have, the more lines you're going to have to graph, which is, again, going to make this thing get very difficult very quickly. So, it's a good method for really simple problems, and perhaps in the days before computers were so ubiquitous, it made sense, but it's not really as practical nowadays. So I'm going to go ahead and stop there.